All right, hello everyone. This is the first part of section 8.3. We're actually going to do 8.3 in 2 days, not one day, so we're not going to shove it in. Our book does it a little too fast, so I'm going to slow down a little bit. You might remember I mentioned in the last video, and then I'm guessing I probably mentioned this in class also in between, that the rectangle idea is pretty important because the rectangles are going to get revolved. So what we're going to do today is called solids of revolution. We're going to take a shape. Let me show you here. We're going to take a shape. Whoa, sorry about that. And we're going to take a curve, the area between a curve and the x-axis to begin with, and we're going to revolve it around the x-axis. So what I'm going to do is take this, oh gosh, a little big, sorry about that. I'm going to take this rectangle. This is why that one rectangle is important. So remember, there's like infinitely many of these rectangles. So in order to find, we're going to take this shape, we're going to revolve it around either the x-axis or the y-axis. And we're going to make a shape. Okay, so I try to draw a picture of it here. It's a little harder to visualize. Looks like some sort of face, but you revolve this curve around the x-axis this way, and you get this three-dimensional shape. And if you think about the three-dimensional shape is made up by adding all these rectangles together, right? So what we're going to do, just like area under the curve where we've added up all those rectangles, we're going to do the same thing. We're going to add up all these rectangles, but we're going to get a three-dimensional shape out of it. So if you can envision this, it's a little hard to visualize, I know. Hopefully you can, but if you take one of those rectangles and you revolve it around the x-axis, it forms a shape, its own shape. And that's what I tried to draw on here. Notice this shape is basically a circle, right? But it's got a little bit of width to it, right? Because the rectangle has infinitely small width because there's infinitely many of these rectangles. We could argue that it has no width. Just think, hey, look, if I take this line and I revolve that line, I spin it around the x-axis, it's going to make a circle. But there's a little third dimension of that circle, which is the thickness of that circle. So what we're going to do is find the volume of each. We call this a disk. It's called the disk method, which you'll see here in just a second. Actually, I don't think you'll see it. I'll write it down for you. It's called the disk method because each one of these rectangles form a disk, like a quarter, right? Like a little coin with a little bit of thickness. So the way we're going to do it, to find the volume of that disk, we're going to find the volume of that little quarter, which is a circle basically with a little tiny bit of thickness, right? So the circle is pi r squared, where the radius of that circle would be however long that purple line is, right there, right there, right there, which I'll show you in a second. And then we're going to multiply it by its thickness, okay? So pi is from the area of the circle, r squared, that r is just the function, right? That r is just that, because when that spins, that's the r, it's just the function. We're going to do this between two curves in just a second. Right now, it's always just one curve. And then the thickness is the dx, right? The little change in x, that thickness of that rectangle, you got this vertical rectangle, that's your delta x. There's your delta x, okay? So I'm going to do one example, and then I'm going to make it the area between two curves. We revolve that, something a little different will happen. So I'm going to do the same thing I did last section. Basically, I'm going to draw a picture. Y equals x squared plus 1. We're going to revolve from -1 to 1, and we're going to revolve this shape around the x-axis. So there's my, what I call typical rectangle. So what we're doing is adding up all these rectangles. Remember, that's what that integral does. So we're integrating from -1 to 1. We got this pi now. Pi times the radius. The radius is just the height of that rectangle, which in this case is x squared plus 1, and times the thickness. That's all there is to it on this one. Now it's just an integral to set up. Because remember what I made a little mistake there, little boo-boo. This right here should be pi times x squared plus 1 squared. It should be pi times the radius squared. The integral is doing Riemann sum, right? It's finding, it's adding up all those areas. So that little formula we have right here, that formula is one disk. The circle, pi r squared times the thickness, the dx. And then the integral's adding them all up. All righty. So here, let's do, we'll do one more example. No, actually, you know what? Yeah, let's do one more example. I'm kind of out of space here. So I'm going to squeeze this one in right here. Y equals x cubed Oh, yeah, let me show you something. Good example. Y equals x cubed, y equals 1, and y equals 8. Okay, so here's my shape. Okay, but now we're going to revolve it around the y-axis. I tricked you out there, right? So in order to keep the shape the same, the disk, we have to draw our rectangles this way, right? Because now my rectangle, visualize the other way, so like this, rectangle went this way, made a disk. This way makes that same disk. It's just all tilted. If we take this and revolve it this way, we get something different. We'll talk about that in the next section. So right now, rectangle always perpendicular to the axis that we're rotating it about. Okay, always, because that makes the disk. So now if I put those numbers in, we get pi times the radius, which is now this way, right? Which is the y cubed. That's all that is. Times my dy, and we're in terms of y, so we're going from 1 to 8.
Okay, folks, sorry, I just made another mistake there. So I'm going to try to fix it real quick. So notice right here where I had y cubed. I made a mistake because this is actually x cubed. So it does need to be in terms of y because it's dy and my rectangles are going this way. But this, since y is equal to x cubed, that means x is equal to y to the 1/3, which means this right here should have been y to the 1/3 for the height of that rectangle, but then I'm going to spin it. It's going to give me that radius. So then I have to square it. So sorry about that little mistake there. I hope that fixes it.
So everything's dictated by the direction your rectangles are drawn. And for now, they got to be perpendicular to the axis. So once they tell you which axis to rotate it around, then you're completely stuck. Okay. And then we're going to do some revolving around other lines also. So what happens if you have the region between two curves? So watch this. I'm going to rewrite these so we can see them. Y equals x squared plus 2. Y equals x plus 2 divided by 2. So I'm going to draw a little picture somewhere. Sorry, I'm kind of out of space here. Y equals x squared plus 2 looks like this. Y equals x plus 2 over 2, which is 1/2 x plus 1. So it looks like this, roughly. Again, a really rough picture is all you need. X equals 0 and x equals 1. So now my region is here. However, notice my rectangle. When I revolve that rectangle around the x-axis, sorry, I didn't say what we're going to revolve about. Revolve about x-axis. All right. Now it's not a disc anymore. It's actually a washer. It's got a little hole in it, right? So if you envision this little rectangle being revolved, we're going to get this. This is called the washer method. The washer method and the disc method are really the same. It's just one case has a hole in it, the other one doesn't. So the way we're going to do this one is just the same way you would have in geometry. We're going to find the volume of the outside circle. We're going to subtract the volume of the inside circle. So it's pi times the outside radius squared minus the inside radius squared. Not the whole thing squared. We take the first circle, pi r squared. We take the second circle, pi r squared, and we subtract them. So for this particular problem, it would be pi. The outside radius, I'm going to try to draw this in. Watch my little laser here. The outside radius goes from here, see the little red laser here, I hope you can see it, to there. That's the outside radius. I could draw that in a color for you. Maybe I'll just draw it in black. That's the outside radius. How long is that? That's the x squared plus 2. We're going to square it. Minus the inside radius. The inside radius will go with brown. This is the inside radius right here. Brown, which is just that other line, which is the 1/2 x plus 1 squared. The thickness is your dx, and we're integrating from 0 to 1. Just power rules again. Factor the pi out, just get it out of there, put it back in at the end. Just don't forget it. It's kind of important. All right, so I got another little example that's going to have something else happen here where we revolve it around a different line. So we're just going to do one more. We'll skip this one. By the way, it works the same as it does for the rectangles or for the area where you can pick either Y or X, which way to draw your rectangles. But remember, we're kind of stuck in this one because we have to be perpendicular to the axis we're rotating around. So we really have no choice. So I'm going to draw this picture again, this one up here, same one here. Same problem we just did, actually. So y equals x squared plus 2. Y equals 1/2 x plus 1. Is it the same? Hang on, let me make sure it's the same. 2y, yep, is it the same? Y equals 1/2 x plus 1 from 0 to 1. But now notice we're going to revolve this thing around something different. We're not going to go around the axis anymore. We're going to go around the line y equals 3. Going to throw a real curveball at you here. So y equals 3. We'll just kind of draw up here somewhere. So now, completely different problem. It's visually very different. This is why pictures are so important. Because if you just think about process, if you think about pi outside radius squared minus inside radius squared, you can just draw a picture to determine what those are. So I'm going to use the black line again for my outside radius. But now remember, my outside radius, if I'm rotating, it's going to actually start here because that distance right there, that becomes the outside radius. Okay, so that distance, I'm going to factor that pi outside. That distance, how long is that line? Well, right here, this little squiggly part right here, that's the x squared plus 2, right? It's the same x squared plus 2. Oh, sorry. Not x squared plus 2. That's the line. So it's actually 1/2 x plus 1. The total distance between the pink line and the x-axis is 3. And then we're going to subtract that little distance. So that black line is actually 3 minus 1/2 x plus 1. It's going to take a couple practice shots at this, I think. Keep coming back to this. You might get a good idea. That's why the picture is so important. Then we're going to minus the inside radius. I'm going to go back to my brown here. The inside radius is that brown line. Notice the brown line shorter than the black line. That's the inside radius. That's that same 3 again, but now it's minus the parabola instead, right? So it's 3 minus the parabola. Whoops, be careful with that. X squared plus 2, all of that squared. Thickness, dx, points of integration, limits of integration 0 to 1, based on what we're given right here in the problem. A little bit harder integral to do because you'd have to multiply all this out, square it, FOIL it out. But again, like I said, you can stop at any point here. You don't have to do the integral. We'll talk a little bit more in class about that. The only problem with not doing the integral is you can't check your answer because your answer in the back of the book is going to be a number, right? Because this is a volume of the shape. So this one might feel a little harder at first. I think once you get some practice at it, it's not too bad. Let me know if you have questions. This is 8.3a. Well, we'll do 8.3b. What happens in the next section is when we revolve it the other direction, where it's not perpendicular. Right now, we're doing always perpendicular to the axis of rotation. Next one's going to be parallel.